Welcome back to Math 1500 Applied Business Mathematics, Connecticut State Community College. We're going to look at logarithmic functions and models today. In recent videos, we've looked at the linear, quadratic, exponential functions, how to model with those and calculate regressions. Today, we're going to look at logarithmic functions and models. Logarithms are things that people don't enjoy as much, but that's okay. We're going to talk about logarithms, what they mean. Basically, what a logarithm is it's the exponent. If I have y equals 10 to the x, if I know x, I can plug x in and solve for y. That's not too hard. When I don't know y, it's a little bit more difficult. We say that 10 is the base of the exponent. When I write this as a logarithm, we write log base 10 of y is equal to x. So 10 is the base of the exponent. It's the base of the logarithm. The purpose of the logarithm is to solve for x. Okay, so I've got a mess on here. To convert this back and forth, basically, if I have, let's just say, 10 to the x equals 27, I'm going to use what I call a curly Q, right? So I've got 10 to the x equals 27, so we log base 10 of 27 equals x. So that comes out as log base 10 of 27 equals x. If I evaluate that on my calculator, you'll notice on the calculator there's a log button here. The base of my log is 10, where this says log, that assumes base 10. Log base 10 of 27 equals 1.43. That means 10 to that power equals 27. Okay, and there's a little bit of rounding going on, which is why it's not exactly 27. On the graphing calculator, there is, if I go to math, you go down to A, log base, and the calculator will pop this up where you could use log base other bases other than base 10. You do log base 5 or something like that. I don't use that as much. I'm a little bit older, a little bit old school. It's a fairly new feature in the calculator. I may use that as we move forward, but that is there for you. So some rules and properties of logarithms: log base b of xy, log base b of x plus log base b of y, or if I've got log base 5 of 3x, we can write that as a log base 5 of 3 plus the log base 5 of x. Okay, I can split things apart. Quite honestly, we use these more algebraic these days because of the functionality on the calculators. And for this course, we just want to be able to see that. I'm going to skip number 2 for a moment and come down to number 3. If I have got log base b of x times y equals the log base b of x plus the log base b of y, that's what's example number 1 or law number 1. Well, suppose that instead of x times y, we had x times x. That would be the log base b of x plus the log base b of x. But the log base b of x plus itself would just be 2 log base b of x, and x squared is the log base b of x squared. Notice that essentially what happened is that this 2 came down in front. That's where we have log base b of x to the r. The r comes in front, is r log base b of x. And I'm going to use that in some of these other rules to kind of show you those, that if I've got the log base b of x divided by y, the log base b of x divided by y, that's the same as the log of x times y to the negative first. Because remember, from exponents, dividing by y is the same as multiplying by y to the negative first. So if I use my rule number 1, that's log base b of x plus the log base b of y to the negative 1. But now if I use rule number 3, that exponent of negative 1 can come down in front, and I have the log base b of x minus the log base b of y. So that's a division rule for exponents. Just a couple of quick rules here. Number 4, the log base b of b equals 1. That's because b to the first equals b. The log base b of 1 equals 0 because b to the 0 equals 1. Okay, so there's some rules here, a little bit less known rules here. The log base b of 1 over x, well, remember 1 over x is the same as x to the negative 1. And then again, I can pull that exponent of negative 1 out in front, and so this becomes negative 1 times the log base b of x. Okay. Number 6 is a change of base rule that is used sometimes, and you see that, and I may refer back to that rule as we move forward. A logarithmic function is a function that's written in the form f of x equals log base b of x plus c, or there might be a times log base b of x plus c. Then you see this other one here which says ln. ln is the natural log, and that's the same as the log base e. That gets used quite frequently in mathematics. Okay, to graph these functions, we've got x and we have f of x. Now we know from the rules up here, I'm going to use rule 4, the log base b of b equals 1, log base b of 1 equals 0. So if x is 1, we know that y is 0. If x is 2, we know that y is 1. Okay? That's because log base 2 of 1 is equal to 0, because 2 to the 0 is 1. Log base 2 of 2 is equal to 1, because 2 to the first equals 2. The log base 2 of 4 is 2, because 2 squared is 4. Okay? So when I go to graph this function, if x is 1, y is 0. If x is 2, y is 1. If x is 4, y is 2. And this graph actually looks like this, where the y-axis is an asymptote. Okay. You've seen graphing on the graphing calculator. Okay, let me prepare this just a little bit. When we did x squared, exponentials 2 to the x, and I graph that, let me hit a zoom 6, that's my standard window, we see the exponential curve, okay? We see that exponential graph increasing. And notice, if I pick a couple of points here, if x is 0, y is 1. Actually, let me go second calc, the value here. If x is 0, y is 1. If x is 1, y is 2, and we would increase exponentially. If I change this to a logarithmic function, okay, we've got log base 2, so I'm going to use that math option A. So we've got log base 2 of x. Notice that that graph is kind of the way that I've drawn it, where, Let's calculate some values. If x is 1, y is 0. If x is 2, y is 1. If x is 4, y is 2. And we can see that graph increasing from there. Okay. Let's fix that, make that blue. So if I made my table of values here, x and f of x, I'm going to use 1, 4, and 16 for x's. That'll give me the y values of 0, 1, and 2. If x is 1, y is 0 because 4 to the 0 is 1. So here's my point 1, 0, 4, 1. I'm going to get all the way out to 16 before I get to 2. And my logarithmic curve looks like this. To double check that, the base is no longer 2, it's now 4. And notice that that's just a little bit steeper, okay? You can play around with the graphing calculator with 3 and 4 for time's sake, and the fact that we don't graph logarithmic functions a lot. I'm going to skip those. I'm going to show where we're going to use logarithms more. If you watched the previous video, when we did exponential functions, you might remember the problem. Suppose I invest $2,500 into an account earning 7.2% interest. That's a 0.072. Earning 7.2% interest compounded monthly for 12 years. How much money is my account worth after the 15 years? That would be 2,500 times 1 plus 0.072 over 12 to the 12 times 15th power. And we got last time 73.3798. What's my investment worth after 15 years, after 18 years, after 20 years, and so on? But suppose I want to know, what's my investment when will my investment be worth $10,000? Now, a couple of things I'm going to do. First, I'm going to calculate this value. The 1 plus 0.072 over, let me get rid of that, over 12 is 1.006. So A equals 2,500 times 1.006 to the 12x, because how long, I don't know x, I don't know the time. When will that equal 10,000? Well, that means if I divide both sides by 2,500, 1.006 to the 12x would equal 4. Now, to solve this for x, I have log this 1.006. This is the base of the logarithm. Log base 1.006 of 4 equals 12x. Go back to blue. So now if I just simply use my log base, math, option A, log base 1.006 of 4 is 12x. So the 12x I know equals 231.74. Now I'm going to divide both sides by 12. X will equal to 1231.74 divided by 12. It will take 19.3 years for my $2,500 investment to be worth $10,000. And if you'd like to check that, we could reuse the formula, but instead of the 15, we could put in the 19.3. So let's do that. 2,500 times 1 plus 0.072 over 12 to the 12 times 19.3. And notice we got, due to rounding, we got right at $10,000. Okay, so I can use logarithms in tandem with exponentials, but the purpose of the logarithm would be to solve for the exponent when I don't know it. Number 6, again, we did this problem last time in the previous video. A equals my $2,500 investment times e to the 0.072 times 15, because my interest is compounded continuously, and we did 2,500 times e to the 0.072 times 15, and we got 61.70. Instead, I want to know if I invest my money in this account compounded continuously, how long will it take my account to be worth $7,500? Now, clearly, it's not going to be much longer than the 15 years, but the question is, if I invest $2,500 e to the 0.072x, when will that equal 7,500? I'm going to divide by 2,500. E to the 0.072x would equal 3. So I've got log base e of 3 equals 0.072x. Now log base e is that ln, or natural log of 3. 0.072x. So I've got the natural log of 3, 1.0986. But now notice, to solve for x, all I need to do is to divide by the 0.072, and x is 15.26 years. That's how long it will take for that investment to be worth $7,500. Okay, so we're going to use logarithms, like I said. If I know the exponent, I don't need logarithms. I use the exponential function to find a. If I know a, but I don't know x, I don't know that time, I use logarithms to go the other direction. Okay? Real quick, logarithmic regression, very similar to the regressions we've done before. T is the number of years since 2000. Spending in billions. This is for research and development by institutions higher education in the United States, what they've spent. Okay, so if x is the number of, or t is the number of years since 2000, so I'm going to go to stat, edit. Let's clear my lists. So we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and our Y list, 41, 45, 48, 50, 52, 54. Whoops, I missed my 52. 54, you always want to make sure you get your data in correctly. 57, 61, 65, 66. Zoom 9 will show us our logarithmic graph, because remember I had my stat plot on, just like in the past. All right, second stat plot. I want my plot 1 on. X list is in L1, Y list is in L2. I like pluses, so a zoom 9 gives us that scatter plot. Okay. So, stat, calc. Previous videos we did linear regression, quadratic regression, We talked about cubic and quartic. Those are just extended polynomial regressions or functions. Exponential regression number 9 is the logarithmic regression. We're going to store our regression equation in y1 again. We're going to calculate that. Now notice y equals a plus b natural log of x. The calculator will always give you the natural log of x. Up here, when I first showed you where to go, the logarithmic equations, notice I had the plus c. I had that constant added last. The calculator gives it to you first. It doesn't make any difference. So the logarithmic function here is y equals 19.45 plus b 17.86 times the natural log of x. Okay. Notice that our r value is 0.97, so that's pretty close. Okay. And if I hit graph now, see how that increases, but the rate of increase is slowing. Because that rate of increase is slowing, right? Plus 4, 3, 2, 2, 2, 3, 4, 4, 1. That rate of growth is slowing. The natural log function, logarithmic graph, seems to work. Okay, so that's why the log function is the best type. In what year would I expect my spending to reach 70 billion? Okay, so my question would be, when do I expect y to equal 70 billion? So I would want 19.45 plus 17.86 natural log of x to equal 70. So I'm going to subtract 70 minus the 19.45. So that's going to be 50.55. Now I'm going to divide by 17.86. So the natural log of x is 2.83. But remember, therefore, that x equals, this is base e to the 2.83 would equal x. So x equals e to the 2.83 power, and that would be 16.95, or just shy of 17 years for my expending, for me to expect that my spending will reach 70 billion. Okay, so there's just a quick look at logarithmic functions. For this course, we talk about them. We don't use them nearly as much as we do the others, but again, I hope that this helps explain logarithmic functions, and I will look forward to meeting you again in the next video. Thank you.